And we are recording. So today we'll be doing the first two labs on minerals, and today's exercises focus a lot more on general identification of minerals and basic diagnostic properties. Next week's lab deals with some minerals that have special properties, like those that are magnetic or those that dissolve in acid, as well as with some of the specific minerals that show up in igneous rocks, because we move on to igneous rocks after minerals, and there are thousands of minerals, but it turns out there's less than 10 that actually make up the majority of most igneous rocks. So we'll focus on those next week. One of them is quartz, by the way, which shows up a lot. But that's more next week's subject than this week's. So again, some of this might be review, but I just want to go through this at the start. What is a mineral? A mineral has 5 basic requirements to be considered a mineral. And a substance that is classified as a mineral must occur in nature. It must be inorganic. It must be a solid. And it must have a specific chemical composition. But the first property we'll talk about is the crystal structure. And a crystal is just a regular geometric arrangement of atoms. On the atomic level, all minerals are arranged in a specific pattern called the crystal lattice. And for something to be a mineral, the atoms have to have a crystal arrangement. So this is obsidian or volcanic glass, which you find in areas that have experienced volcanism. It forms when magma cools really, really, really quickly, so quickly, in fact, that it doesn't have time for the magma to crystallize and form minerals. So this is an approximation of what obsidian looks like on the atomic level. And is there regular spacing between these? Like, are all these kind of loops made by the atoms the same size? No. This is also more or less what glass looks like under a strong microscope, like at the atomic level. Glass is not crystalline either. Glass is kind of just, the atoms are just kind of scattered wherever, and some might be farther apart than others. So that's why glass, whether it's window glass or volcanic glass, is not considered to be a mineral. So this is an example of what a crystal lattice looks like. It's a very simple one. This is just rock salt. Rock salt, salt like the salt that we put in our food, is actually a mineral. And the fun thing is that whether you have nicely formed large crystals like this or just the little grains of rock salt, the sodium atoms are going to alternate neatly with the chlorine atoms. This structure is present in both these big crystals, and the structure is also present in these little crystals. The crystal structure is something that is inherent to a mineral, whether or not you break it into tiny pieces or not. Now, if you were to heat it up, it could change. But if you're just breaking the mineral into tiny pieces, it's still going to have this crystal structure, which is something actually that happens with sand also. Most sand is made from quartz, and the same structure in large quartz crystals is also present in just the tiny grains of sand. But halite is a pretty simple example of a crystal lattice. There's nothing in rock salt besides sodium and chlorine, some impurities maybe, but the chemical formula is just NaCl. So it's a really nice, simple example of a crystal lattice where you just have the two types of atoms alternating, and this one chlorine atom is going to be the same distance from a particular sodium atom as any other chlorine atom is. This is going to be repeated throughout the crystal, whether it's a big chunk of it, like this nice rock salt, or whether it's the tiny broken up pieces you'd have in your salt shaker. So, questions so far? So, many things are crystals. There are some things that are crystals that are not considered minerals. One example of that actually are the artificial crystals that humans engineer for use in medical technology or to work with lasers. Lasers actually often need crystals with specific properties that are not easily found in nature. So humans have synthesized a number of crystals with chemical formulas that do not exist in nature. So this is an interesting crystal that has neodymium and yttrium and vanadium in it. And this crystal does not exist in nature as far as we know, not in significant amounts at least. So it's not actually technically considered to be a mineral because it doesn't already exist in nature. And to an extent that can feel like hair splitting, but it's mostly just meant to exclude man-made substances from the list. We treat the study of rocks and minerals as the study of natural occurrences, and we kind of don't focus as much on stuff that only exists because humans have made it. But artificial crystals are really interesting from an engineering perspective. And they also often have elements like yttrium that you don't commonly see in the chemical formulae of regular crystals. In fact, that's one reason yttrium is not very common. This is from yttrium that people have concentrated and artificially put into this crystal. So that's another part of it. It involves humans mining and artificially concentrating elements like neodymium and yttrium that are really rare. And here's another example of something that may or may not be a mineral. So let's talk about what the inorganic part means. Who here has friends taking organic chemistry? Anyone have friends in OChem? I don't know how that's really happening online, but this thing didn't get muted again, did it? Would somebody say something just so I can confirm this isn't muted? Phooey.
You're not muted.
Okay, fantastic, fantastic. Okay, I apologize for that confusion. Thank you. Sorry, now I'm paranoid about that because that happened that one time and I felt bad. But so if you know anyone taking organic chemistry, it is basically studying the horrifyingly large number of combinations of different chemicals that all sound the same and the formulas look the same, but they have different numbers of double bonds, different numbers of carbon, different numbers of hydrogen, and they all have different properties as a result of that. Organic chemistry is really interesting, actually. I took OChem when I thought I was going to be a chem major, but it's funny because it's one bit of my chemistry background that has not been very useful for geology because minerals can't be organic. Minerals are, by definition, not organic. They do not contain carbon-hydrogen bonds. So this is one thing that's sort of tricky because people sometimes interpret this as, oh, it's organic, so minerals can't have carbon in them at all because carbon is organic. And it's not the presence of carbon itself. There's some minerals that are made up of just carbon. What's one example of that, actually? So actually the lead in your pencils is not actually lead, thank God, because lead is horrifically toxic. It's actually graphite, which is pure carbon, which is technically considered a mineral. So graphite is a mineral. Diamonds are also made of pure carbon, just they form under extremely high pressure and temperature. They're not organic because there's no hydrogen in them. But something like a crystal made of sugar. Sugars are all carbon-hydrogen bonds. Sugars are what people studying OChem are learning about to a big extent. So rock candy is what you get when you make sugar crystals. It has crystals, but it's sugar, which has lots of compounds with carbon-hydrogen bonds. So is rock candy going to be a mineral then?
Yeah, isn't it?
Close. It's not because the sugar is organic. The sugar has carbon-hydrogen bonds, so that alone makes it not a mineral. Yes, it's a solid. Yes, it's a crystal. Yes, it does have a specific composition, but it's made of sugar, which is organic. So it's a little bit of hair splitting, and the organic thing does get a little more complicated when you get into more advanced geology and start talking about the fact that some minerals are synthesized in the bodies of shellfish in particular. We're not really going to worry about that distinction here, but if it has carbon hydrogen bonds, which sugar does, which methane does, this is the other greenhouse gas, the stinky one that's coming from all the bogs and from cows farting, but that's also an organic compound, but not minerals. Does that make sense? Anybody have any questions so far? So a mineral has to have a crystal, it has to be naturally occurring, it has to be inorganic, and it has to be a solid. And the main point of confusion that comes up here is that people are often uncertain as to whether magma is a mineral, because rock, which contains mineral, comes from magma. And the way to think about magma is that it's kind of a proto-mineral. It's kind of like when you have cake batter. It's not cake yet, but when it solidifies, it's going to become cake. Magma has all of the chemical compounds in it needed to make minerals, but those minerals haven't formed just yet. The minerals have to be a solid, and a liquid magma will form into minerals when it cools, but it's not considered to have minerals until any of it becomes solid. So a magma is not a mineral, but crystals will cool from the magma. Something we'll return to more next week is that as the magma cools, different minerals start to crystallize from the elements present in the magma in a certain order, actually. Certain minerals crystallize first. And eventually the magma will cool completely into minerals. The composition of a magma changes over time as some of it starts to crystallize into more minerals. But the part of the magma that's liquid itself, like the background color in all of these is meant to represent the magma that's left. You have some crystals forming here, and then more crystals forming to join the others here, and so on with steps 3 and 4. But the part that's liquid does not have minerals in it. It has the starting substance. It has the materials needed to make minerals. It has silica and iron and magnesium in it, but it doesn't actually have the minerals formed yet itself. And then the last aspect is that a mineral has to have a specific composition. So that means that we can come up with a formula for a mineral that's going to describe chemically what is in any sample of that mineral. We're not going to be learning a lot of chemical formulas for this class. I'm not really focusing on it. But it's good to become familiar with a couple of common ones, like quartz is just SiO2, which is a pretty simple one. And then you have a couple minerals like gold and salt that are pure elements. Yes, I heard a question.
Mariana had a question in chat.
Interesting. I cannot see the chat right now, and the notifications are not coming up strangely.
Well, I was just asking if you said that, it was just trying to jot it down for notes. You said inorganic don't have chemical bonds, or what was it that they
don't have carbon-hydrogen chemical bonds.
There you go. Okay, thank you.
Yes.
Carbon-hydrogen?
Carbon-hydrogen, yes. Because most organic compounds are largely a combination of carbon and hydrogen. They're sometimes going to have nitrogen and oxygen too, but organic chemistry is all about hydrocarbons, as they call them. And minerals are not hydrocarbons. Cool. And I am sorry, I don't know why the chat, it's not even giving me notifications, strangely enough.
I think it's because you're sharing your screen. Whenever they share screens, you can't see chat box.
Interesting. I feel like I have been able to see that some other times, but
yeah, I thought that too. But most of my other professors, when they're screen sharing, they're like, "Oh, please voice your question," because they can't see the chat box right now.
Okay, cool. So
might be something in the settings.
That is a good thing to remember. I will play around with the settings after we do this. But yes, you might, if you can only use chat right now, maybe you can find a way to have a classmate to message a classmate and ask them if they can voice the question. But anyway, I'll be able to see the chat questions after this is done. So I apologize for that. Any other questions I might have missed from not noticing the chat notifications? Okay, cool. So chemical composition. Minerals are going to have a definite chemical composition. You will sometimes see with feldspars and some other minerals, you'll see elements in parentheses, like you'll see like calcium, comma, sodium in parentheses. And what that means is that there are known variations within that mineral where sometimes it may have more calcium and sometimes it may have more sodium. That's not something we're going to focus on much, but if you take further classes and start looking at mineral chemical formulas in context, that it still is considered to have a definite chemical formula because scientists know that only those two elements are going to be part of it, or that are going to be part of the formula in that way. But it's a little more complicated than the chemical formula is always the same. But minerals are going to have a definite chemical formula of some type, even if there is some known variation in it. And a lot of the common igneous rock forming minerals are based on silica. So quartz is commonly found in igneous rocks, and it's just SiO2. And quartz, honestly, is actually what just happens to the leftover silica, because the silica gets taken up by lots of other minerals that go into igneous rocks, like olivine and pyroxenes and feldspars, and then the leftover silica ends up in quartz. Now, speaking of quartz, I would like to make you think about sand. And sand is something we'll come back to more when we talk about sedimentary rocks and sediments. But sand is not a mineral in itself. Sand actually refers to grain size. Sand refers to pieces of sediment that are smaller than gravel, but larger than silt. And it's like beach sand texture, something with sand-sized particles. You can still feel the individual grains, but you can't see them as well, and you have to look closely. You have to look closely to tell one piece of sand apart from another. This is very pure quartz sand under a microscope. And it turns out that sand can have many different minerals in it. Many different minerals can be broken down to sand size. And so, well, the vast majority of the sand we find on the beaches is made of quartz. Outside of the purest examples, there's usually going to be other minerals mixed in there. This is an example of really pure quartz sand, but the sand you find on the beach is often going to have fragments of other rocks and other minerals in there, unless it's been very heavily weathered. And then some sand is not going to have quartz in it at all. Does anybody happen to know where this is? It's a national monument in the US. It is a national monument in New Mexico. It's White Sands National Monument, and the sand is named because it gets this really pure white pearly appearance from being made of gypsum, which is a completely different mineral from quartz. So gypsum looks like this in hand sample, like when you have a larger piece, and quartz looks like this in hand sample when you have a larger piece. Both of these two separate minerals can be broken down. Yes?
I have a question. When you see like pink sand of the beach, I don't know where in the world it is, but there's like pink sand beaches.
That's a really
What is that from?
That's a really good example. The pink sand beaches have a lot of alkali feldspar in them, and it's a variety of feldspar that's kind of pink colored because of the potassium in it. So pink sand beaches are beaches that have a lot of alkali feldspar mixed in with the quartz. So that's a really good example. There's another mineral present that's giving it a different color. Same is true of black sand beaches. Black sand beaches form when you have volcanic rocks breaking up very close to the ocean. And so darker minerals weather out faster. They're weak. Which is something we'll talk about a little bit later. But the black sand beaches form when you still have a lot of the olivine and the pyroxene and the other darker minerals still present, along with the quartz. So pink sand beaches are a good example, and then black sand beaches are a good example. And then white sands doesn't have quartz in it at all. White sands is from large deposits of gypsum weathering and breaking down into sand-sized pieces. And you end up with the same, more or less the same texture, just from a completely different mineral. So that's something to consider when we get more to sediments and to sedimentary rocks. The terms like sand or clay or boulder don't really tell you much about the minerals or the rocks that sand or boulder came from. They talk more about the size of those pieces. So what about ice? This might be a question that you've been asked before, but I want to ask you if ice is a mineral. And remember, a mineral has to be crystalline, solid, inorganic, naturally occurring, and definite chemistry.
Yes.
Yes, it is. Yes.
Cool.
Ice is a mineral. Ice is a mineral because it doesn't have any CH bonds. It's solid. It occurs naturally, like in this. This is one of my Antarctica pictures, actually. These are my colleagues arguing over rocks, and I decided to take glacier pictures in the meantime. H2O. That's probably the first chemical formula you ever one learns in their lifetime, honestly. And the thing is, water is not a mineral, but you can kind of think of water as being kind of like magma for water. Water is the liquid that, if the temperature drops enough, can crystallize and solidify into a mineral, the same way that magma can crystallize and solidify into minerals and into igneous rocks as a result. Obviously, it's a very different temperature involved. Ice is going to melt at a much lower temperature than rock is going to melt, not at dangerous temperatures also, but ice is a mineral. And so that's an overview of what a mineral actually is, and a little bit about what a mineral is not. Any questions about the preceding slides or about what defines a mineral? And I do realize with some of the counter examples, it might seem kind of arbitrary, like, okay, it's a crystal, but it's human made, so it's not a mineral. Yes, it is a little bit arbitrary. A lot of it is, again, to come up with a workable definition at all, and to also kind of establish study of minerals as study of naturally occurring substances. Now, there are thousands upon thousands of minerals, including some that haven't been discovered. Most minerals are pretty rare, though. A lot of the new minerals that are being discovered are often found in one vein somewhere. And over time, it gets pretty easy to identify some of the basic minerals, some of the more common minerals, as you get practice. And I do want to emphasize that if some of this seems difficult at first, a lot of this comes with practice. I have felt that even by teaching these classes over and over again, my mineral identification has gotten better. And a lot of introductory mineralogy is learning basic mineral identification that's going to be helpful in the field if you're scouting, because we also really heavily use geochemical methods to distinguish and study minerals at this point. So we use microscopes, we use mass spectrometry, we use we grind the rocks up to measure them via X-ray fractometry, but those are all tools that don't get carried into the field very well. They involve large machines and they involve very clean lab conditions. So if you're out in the field, it's really helpful to be able to do basic mineral identification based on the properties we'll go over today. And minerals in the field are going to be defined by their color, their luster. So that's how they reflect or don't reflect light. Their streak, which is the color left behind when you grind the mineral on a porcelain plate, how hard the minerals are, and their cleavage, which is always the Beavis and Butthead moment of intro geology classes, but it refers to how minerals break. And next week's lab, we will go over some of the other properties that are helpful for a few specific minerals. These first 5 are going to be useful for most minerals. They are useful in varying degrees. Cleavage is actually, in general, one of the most useful properties because it relates to crystal structure and tends to be very diagnostic. So we'll start with the color of minerals, which actually is not always very helpful. So these are actually all the same mineral. These samples all belong to the same mineral, calcite, and this lower sample here is what calcite looks like when it's in its purest form. And when I say pure, I'm actually indicating that these other samples have stuff in them. They have impurities. And color is often misleading because a lot of common minerals like quartz and feldspar and most types of feldspar and calcite are colorless or white. And that means that they are very, very easily stained by tiny amounts of impurities like manganese or cobalt or copper. And they're called impurities because they're present on the parts per million or parts per billion level. There's not enough of it present to be considered within the chemical structure. But it's kind of like with stained glass. Stained glass is colorless to begin with, and a small amount of impurity in stained glass actually gives it its color. You don't need to put a lot of copper in stained glass to make it blue, and they actually do use copper and cobalt to color stained glass different colors. So all of these are calcite, but the pink one has manganese in it. I know for sure. I'm not as sure about some of these other ones, but different metals, when bonded to other atoms, will give calcite these rainbow colors. And so calcite, this particular mineral, is not easily identified by color always because it's very easily stained. Something we'll come to later is that calcite is very well defined by cleavage. It breaks in a very particular way, and so that ends up being a much more useful diagnostic property. Sometimes color is helpful, though. You can learn over time when color is actually going to be diagnostic for a mineral and when it isn't. So these are 2 minerals that I can spot at first glance now, partially because I'm a geologist, but also because there was a lot of these 2 minerals where I was growing up. And these are azurite and malachite, which you often find around copper mines because they contain copper. We normally think of copper as being, well, copper colored, like a sort of brown colored, but when the element copper is bound to other atoms, it actually produces blues and turquoises and greens. The brown copper is what copper looks like in its pure elemental form, but as soon as it bonds to other atoms, it ends up giving a different color. So these minerals are really easily identified by their colors. Azurite and malachite, they also often occur together. And sometimes you can also learn what impurities cause which colors. Manganese pretty much always causes this really beautiful rose color. So rose quartz is caused by small amounts of manganese being present in quartz, which is otherwise just silica and oxygen and is normally colorless. And the same is true of a variation of calcite that has the pink color. Questions so far? So the takeaway is with minerals, be careful with the color. Don't jump to the color to instantly identify what something is. I will say that when we get to igneous rock forming minerals next week, there is often a good distinction between mafic minerals, those that are colored dark or those that are colored gray, those that are colored dark green, and felsic or light colored minerals like white and gray minerals. And those distinctions do tend to be a little more set in stone. The black minerals that make up igneous rocks tend to stay black no matter what, but that's something we'll get to more next week. So the luster is a property that I find quite subjective, and I find that different books and different methods describe it differently. But in short, the luster is how a mineral reflects light. And the most important distinction is usually going to be between minerals that have a metallic luster, like this pyrite or fool's gold, and those with a non-metallic luster. And if a mineral has a non-metallic luster, that means that at least some light could possibly pass through, especially if you were to grind the mineral down to a single layer, like a single sheet. And metallic lustered minerals reflect all light. No light can really pass through minerals with metallic lusters. And even if you were to reduce this pyrite to a single layer, it would still reflect all the light back. Whereas a lot of these other minerals are, you can see through them if you cut them thin enough. So with the non-metallic lusters, sometimes it's a bit subjective. I would say go by the terms introduced on Canvas for the Canvas exercise. Don't try to compare this diagram with the ones on Canvas and get mixed up. But this is just one example of how one can define a number of non-metallic lusters. So you have minerals that are kind of dull, minerals that are kind of vitreous, and vitreous means glassy. You have to be careful with glassy minerals to not confuse that for metallic, because glassy minerals, you can kind of see there's a little bit of a reflection on them. Well, actually, that's not what I meant to say. You can see that they're kind of glassy, and if you cut them really thin, you could hypothetically see what was on the other side of it. You have to make sure that you can tell if a mineral kind of looks glassy or whether it looks metallic. And learning the difference between metallic and glassy helps a lot with studying luster. And adamantine luster is kind of just a specific version of vitreous luster. Quartz is kind of glassy, diamonds are glassy. A lot of minerals we study are kind of glassy. You also have some minerals that are silky, some that are more greasy, like chrysocolla, which is a copper mineral. Earthy, like azurite, which we just saw earlier. Some minerals are more pearly. Some are even kind of waxy. I'd say feldspars are pearly. Some of the other igneous minerals that we'll talk about next week have more of a pearly luster. None of the major igneous rock forming minerals have a metallic luster. Metallics tend to be either gold or silver or other native elements, or oxides that form usually alongside gold. So you get fool's gold forming in mineral veins, often relatively close by where there's been gold deposits, but it doesn't have gold at all in it. It's a sulfur compound. Questions about luster or about any of the other properties we've gone over so far?
What's the one that says dull luster? What?
Microcline feldspar. Microcline feldspar is one particular type of feldspar. And that means it's just kind of chalky looking. Like it doesn't really shine at all. And that is something you have to be careful about. A lot of minerals are kind of shiny, but not all of them have quite the metallic shine. But there's some minerals that don't really shine at all, and so they're just described as having a dull luster. And these are kind of very qualitative terms, and that's specifically done so that minerals can be identified in hand sample and in the field. The luster can be useful for telling apart minerals of the same color in mining areas, or confirming that a specific ore mineral is the one you want. I will say it's not going to come up as much with the minerals that make up igneous rocks. It's not as important a distinction, but we do go over it here. Other questions?
What colors did you say that the metallic luster comes in?
What colors? The metallic luster can come in many different colors. So it can be gold or silver. You can have kind of sort of dark metallic colors. I can't think of any specific examples of like a blue or pink mineral with a metallic luster. So that's the thing. Metallic luster minerals are also usually going to have metallic colors also.
Mm-hmm.
Are we good to move on, or any other questions? So luster is how a mineral reflects light. Then streak is what color a mineral produces when you grind it across a porcelain plate, which is another place where the tactile element is kind of lost here, because it's fun to actually take the hand samples and crush them on the porcelain plate and see what color comes out. So some minerals leave a distinct streak behind, like cinnabar and pyrite leave distinct streaks behind. And pyrite looks kind of gold, but its streak is actually more gray. And the interesting thing about streak is that not all minerals leave behind a streak that looks that similar to the color that we observe when you have a large piece of the mineral in your hand. And that's what I mean by hand sample. A hand sample is when you have like a piece of the mineral that you could hypothetically pick up and test out. As opposed to, say, a thin section, which is when you cut a single layer and put it on a microscope slide to look at. But not all minerals leave a distinct streak. So streak is not always going to be all that useful. A lot of the igneous rock forming minerals simply leave behind a white or colorless streak. And also, the streak plate itself is softer than some minerals. Some minerals are actually harder than the porcelain streak plate itself. And if you crush the mineral into it, it will actually cause the porcelain streak plate to break up, not the mineral itself. So that's the thing to consider. Only some minerals leave a distinct streak behind. It's useful for a lot of oxide and sulfide elements that you find in hot springs or find in the veins where you find gold and silver. And really kind of what's happening, the reason why the color's different sometimes is because there's going to be a difference in how the light makes it appear if you have basically a single layer of the mineral, which is what's going on the streak plate, versus a big chunk of the mineral. And sometimes the streak can help us determine a mineral diagnostically if the hand samples are kind of beat up and if it's hard to tell exactly what mineral it is. But streak plates will not always be useful, and the hardness of the mineral has a lot to do with that. So geologists developed a simple scale for measuring the hardness of minerals out in the field called the Mohs hardness scale. And it's meant to be based on objects that you might have on you, or that you could come across pretty easily. Like, assuming I never paint my nails because I'm a geologist at this point, but assuming you're fine having your fingernails scuffed up a little bit, a fingernail actually has a defined hardness on the Mohs hardness index. A fingernail has a Mohs hardness of 2.5, and so there's some minerals like gypsum and talc that are softer than your fingernail, that you can, if you crush your fingernail into them, the mineral will break up. Your fingernail will not be scratched. And that's kind of what the Mohs hardness index is based on. It's based on a system of what scratches what. Outside of your fingernail, it uses copper pennies and either a knife or a glass plate, because those have about the same hardness, and steel nails as reference. And this particular version also lists a masonry drill bit at 8.5. I haven't seen all versions do that, but that is thrown in there to help test out some of the really hard minerals, because as I mentioned before, the streak plate is there are going to be some minerals that are harder than the streak plate. The streak plate has a hardness of 7, which is also actually the hardness of quartz. If you try to crush quartz on a streak plate, it's not going to leave a streak. Neither mineral is going to disintegrate because the quartz and the porcelain are the same hardness. And to use the most hardness scale, you use objects like the steel nail or the copper penny to scratch the mineral, and you look closely and see what has been scratched. If you're scratching a penny on a mineral and the penny is harder than the mineral, the penny is going to physically damage the mineral and cause the mineral to be ground into tiny pieces. But if the mineral is harder than the penny and you grind them together, the penny is actually going to be what's scratched. And when I've taught this lab as an offline lab, what I've found that I have to remind people to do is to look very closely at whatever you're crushing the mineral on, and be very sure of what is being crushed up, whether it's the mineral that's breaking up or the nail that's breaking up. I've seen some people, for example, one of the most common igneous rock forming minerals is hornblende, which has a most hardness of 7, I think. Anyway, it's harder than a steel nail. And people would crush the steel nail into the hornblende, and they would see like the silvery color forming, and they would think that the mineral hornblende was breaking up. That was actually the steel nail being broken up. And if you look closely, sometimes you can see the color of what's being broken up. I had to remind them, if it was the mineral breaking up, that mineral is black, you would see black powder. You're seeing kind of a gray silver powder. That's because this mineral is harder than the nail. And when you crush this mineral into the nail, it's actually the nail that's breaking up into tiny pieces. So you can also test other minerals on each other. But it's a reference scale to order how hard minerals are without having to do tests on the mineral and come up with like an internal number system. It's a relative system designed to help you compare the hardness of minerals to relatively common objects that you might hypothetically have on you while you're doing research. And geologists will often bring a streak plate with them because a streak plate helps you determine the streaks of minerals if you're trying to say look at sulfides in a mining area or something, and it can also help you determine the hardness because a streak plate is hardness 7, so that's also a very useful reference. So any questions about hardness or any of the other properties before I move into fracture and cleavage? Okay, so cleavage and fracture are different ways in which minerals break. So this is all about what happens to minerals when you actually physically damage them. Because one thing I find that people get confused about with cleavage and fracture is they confuse cleavage with crystal form. They confuse the shapes that form when you smash a crystal to the form a crystal has. And something I'll mention is that some crystals that form really beautifully geometric shapes, like quartz, don't actually have cleavage. They don't form a regular pattern when you break them. Some minerals do form a regular pattern along planar surfaces when you break them. Cleavage involves breakage along flat planar surfaces. So a mineral with cleavage is going to break along those planar surfaces in a certain way, and that has absolutely nothing to do with what the crystal looks like when it's growing. Now, if a mineral forms more of a jagged or a curvy shape when you break it, it's not said to have cleavage, it's said to have fracture. Fracture just means it's breaking in an irregular pattern. And sometimes you get this rather pretty pattern, these sort of circular curved breakage patterns. That's called conchoidal fracture. And conchoidal fracture is not the same as cleavage, because conchoidal fracture doesn't really occur along a regular system. It just means that the mineral tends to break in more of a curved pattern instead of a jaggedy pattern when it gets broken up. So quartz does not have cleavage. Also obsidian, which is not a mineral, but it's a glassy substance that does exhibit fracture, conchoidal fracture, where you get these curvy patterns, but it doesn't break along straight lines like some of the other minerals we'll look at. Does that make sense? I'm going to go over a couple of examples, but does the definition of cleavage make sense to people?
Yes.
Okay. And here's another example of what I mean when I say that crystal form does not equate cleavage. This is garnet, which when it has time to crystallize forms really beautiful crystals. Some sand has a lot of garnet in it, depending on where that sand is from. And I used to look for what are called sand rubies, which are tiny garnet crystals when I was a kid that you sometimes find. But if you actually smash a garnet crystal, it doesn't cleave along flat planes. It makes this jaggedy, rubbly appearance. So it has a nice crystal form, but it doesn't have any cleavage. And quartz is the same way. But some minerals that do have cleavage are micas. And micas are said to have one plane of cleavage because when you break micas up, they form these sheets. Micas are really soft, and you can actually peel them so that you have these layers of the same thickness coming off, but the edges of, if you think of these sheets as kind of like sheets of paper, the edges of the sheets aren't really regular. The edges are kind of jagged and don't really break off in any particular pattern, but you can peel them off in regular layers. The sides don't break regularly, but the top peels off regularly. And muscovite and biotite and some other important micas we'll learn about are like this. And micas have one plane of cleavage. Some of the other important minerals are said to have two planes of cleavage because when you break them, they break regularly on the top and on the side, but not the front and back. They break regularly in 2 dimensions, but not the third. And it is kind of helpful to think of cleavage planes as being in dimensions. Micas break along 1 dimension, and feldspars break regularly along 2 dimensions. So when you smash a sample of feldspar, or pyroxene, which is another mineral that does this, the broken off pieces are going to be somewhat rectangular. You're going to have a smooth, and actually cleavage surfaces are often, they're noticeably defined by being smooth and kind of shiny because it's a regular, relatively clean break. I'm going to jump back to the mineral, to the one plane. You can see that with mica. You get these smooth, shiny surfaces with the layers of mica, and it's not always as well defined, but you get smooth, shiny top, and the bottom is smooth. It's just on the table here. And then the sides are also relatively smooth and shiny. But then do you notice how the front is kind of rubbly? And that's true of the back, which is just hidden from view here. In 2 dimensions, you have these shiny flat surfaces, but then in the 3rd dimension, it's not very regular and the surface is kind of rubbly. And that's why feldspars aren't said to have 3 planes of cleavage. The regular breakage only occurs in 2 dimensions. Now, one thing we're interested in with cleavage is that if there's more than one plane of cleavage, we want to know what angle those planes meet at, because that's also often a very useful mineral identification. So minerals that give you more of a boxy appearance are going to have those planes meeting at an approximately 90-degree angle. It's not always going to be quite 90, but it's close enough to give it a very boxy appearance. It's a little harder to see here with the pyroxene. The smoothness of the layers is not quite as well defined, but this is a plane of cleavage on top. This is a plane of cleavage on the side, and they meet at a 90-degree angle here. The front is in shadow, but it's all rubbly and messed up. Questions? So these examples have 2 planes of cleavage that meet at 90 degrees. There are some minerals that have 2 planes of cleavage where they do not meet at 90 degrees. So hornblende, which is an igneous mineral that we'll talk about more, has 2 planes of cleavage that kind of form more of a rhombus shape. You get 120-degree angles and then 60-degree angles. And here, we're not looking at a cleavage plane. We're looking at the sort of rubbly 3rd dimension. There's a cleavage plane in 1 dimension, like on this side of the rhombus, and then there's a cleavage plane in this dimension on the other side of the rhombus. But the surface we're looking at straight on, and then the surface that's opposite, is not a cleavage plane. Hornblende doesn't break regularly in 3 dimensions. So sometimes 2 cleavage planes meet at a not boxy angle, and you can sometimes have 3 or more cleavage planes, and they may meet at 90-degree angles to form more of a cubic shape, or they might make more of a rhombus. So the difference between this mineral, calcite, and the minerals you were looking at earlier is that you only see smooth surfaces here. The front is smooth and so is the back. The sides are smooth and the top and bottom are smooth. Calcite has very well-defined cleavage, and when you break calcite up, often you can just find lots of calcite crystals in limestone quarries, and you can actually, I've done this. I've taken a hammer to a large piece of calcite, and these little fragments will kind of just fly off, and they look kind of like teardrops almost, because I don't know what it is, but it looks like a bunch of droplets of water almost flying off all at once, and they're all approximately the same shape. They break regularly along these cleavage planes, and you form these nice little rhombus shapes. And then rock salt or halite has 3 planes of cleavage, and the planes all meet at 90 degrees, so you have more of a boxy shape. And halite forms really interesting forms sometimes. Something we don't really go into in this class is that you get crystals twinning and crystals growing in interesting shapes. You can also have more than 3 planes. We're not really going to go into it, but this is sphalerite, which actually has 6 cleavage planes and is said to have dodecahedral cleavage. And some minerals have no cleavage at all, including some minerals that look really nice when you have large, well-formed crystals of them, but when you smash them, they have only conchoidal fracture. So that's true of olivine, and that's true of quartz, both of which are common in igneous rocks. So the next couple slides go over the lab. Does anybody have questions about this material? About mineral identification properties, about what makes up a mineral, about anything else I might have gone blah, blah, blah about? Cool, so I'll be around for questions, obviously, but let's talk about the lab a little bit. So this is what your mineral tray would have looked like if you'd actually gotten to do this in person. So for this lab, you are going to be doing your best to make do with a picture, and this is the same exact photograph that is on Canvas. I realized that some of the numbers are covered up. Just to establish it, it goes 1, 2, 3, 4, then 5, 6, 7, 8, then 9, 10, 11, 12, then 13, 14. And if you need to clarify with me what a specific mineral is numbered, I'm happy to do that. But just be careful not to lose points because you misread what a mineral was labeled as. And there's a lot more you would learn from handling a mineral and looking at it closely versus looking at a picture and trying to watch some videos. I do want to say watch the videos that go along with each exercise, because they are one of the few things that does bring any sort of tactile, like handling the minerals back to this. And it kind of shows you what people actually do, like how you would scratch the minerals if you were going to do this as a live class. So there's questions that focus on the colors of the minerals, on cleavage, on streak, on luster, on hardness. These slides are uploaded, actually. I went ahead and did that before class if you need to download them on Canvas and reference them. Next week's lab will focus more on some of the minerals with special properties, and pay attention to some of the minerals that I talked about a lot in this lab, like quartz or feldspar, because those will come up more next week. And as for what's due next week, this first part of the lab, and there's no upload window this time, it's just a quiz, so you don't need to worry about uploading a separate part of it. It's just answering the questions in lab 3A. So this is to be turned in before next Monday. There is also a lab quiz on the 2 plate tectonics labs we did. Just as with the quiz you had on maps, it's going to be a review quiz. You are welcome to reference you're welcome to look at lab 2, and it's a short quiz. That's due before next week at all. Excuse me, that's before next week. That's due before next week as well. And also, if you have questions about mineral ID or whether something has 2 planes of cleavage or not, please shoot me an email. And I also can meet by appointment if you end up coming up with questions after we finish the lab period. Does anybody have any questions now before I shut the recording off? Okay, I'm going to stop the recording and the screen share, and